Welcome back to Physics Online Crash Course class. Today we will be discussing some neat applications related to kinetic theory of the gas. In case of that kinetic theory of gas, which deals with the study of kinetic interpretation of pressure and temperature. By taking use of that Boyle's law, I can write the equation P1 V1 divided by N1 into T1, which is equal to P2 V2 divided by N2 into T of 2. So PV, which is equal to constant, right? Then I have to write the expression for that pressure here. Pressure I can write it as pressure P, which is equal to N by V KB into T in terms of Boltzmann constant N by V. So into KB into T, or this pressure equation I can consider as, so in terms of mass I can consider rho by M R into T. So this is one more expression for the pressure. Now when the gas molecule is placed in case of that cube, then I have to find out that what is pressure exerted by the gas molecule on the wall. So pressure exerted by the gas on the wall we can consider. Pressure exerted by the gas is, so generalized formula, pressure exerted by the gas, pressure exerted by the gas is, right? So pressure exerted by the gas, pressure P, which is equal to 1 by 3 N into M into V bar square. This is the required expression for pressure exerted by the gas on the wall. Here N stands for number of molecules and M stands for mass, and V bar square means this is nothing but mean speed we can consider. So V bar means mean speed of the gas molecule or average speed of the gas molecule I can consider. And this equation I have to write in terms of density. In terms of density, so pressure P, which is equal to 1 by 3, so N into M, so this is rho into V bar square. So pressure exerted by the gas molecule in terms of density. This is the connecting formula here. Now I shall relate that kinetic energy per unit volume and pressure. What is the relation between kinetic energy per unit volume and pressure exerted? Relation between kinetic energy per unit volume and pressure. What is the relation between kinetic energy per unit volume and pressure? Pressure, which is equal to 2/3 of the kinetic energy per unit volume. So how to remember this equation? It's enough. So pressure, which is equal to 2/3 of the kinetic energy per unit volume. Then kinetic energy in terms of temperature we can consider. Kinetic interpretation in terms of temperature. Next we can understand that one more form. Kinetic interpretation in terms of temperature. In terms of temperature. Kinetic interpretation in terms of temperature. Kinetic energy, which is equal to 3 by 2 times of KB into T. So it means that kinetic energy directly proportional to temperature. Kinetic energy, which is equal to 3 by 2 times of KB into T we shall consider, right? So then in case of that kinetic theory of gas, we have to understand that speed of the gas molecule. Those speed of the gas molecule I can consider as average speed, root mean square speed, and most probable speed. So look at here, the speed of the gas molecule I can categorize as First thing is average speed. Average speed, right? V bar I can take it as average speed. Average speed means it is the arithmetic mean of speed of the all gas molecule, you can call it as average speed. It is the arithmetic mean of speed of all the gas molecule, you can call it as average speed. And for this average speed we are having the formula square root of 8 times of kb into t divided by pi into m, right? So one more form I can consider, which is equal to 8 times of kb into t, which is nothing but r into t divided by pi into, right? So one more form, pv, which is equal to r into t, right? 8p into v divided by pi into m. So these are all the required expression for average speed, right? Arithmetic mean of speed of the all gas molecule, you can take it as average speed. And next one is root mean square speed. Root mean square speed. So this we can take it as VRMS, root mean square speed. So root mean square speed means it is the square root of root mean square speed, which is the square root of mean square speed of all the gas molecule. Mean square speed of all the gas molecule, we can call it as root mean square speed. It is the square root of mean square speed of the all the gas molecule, you can call it as root mean square speed. And equation for root mean square speed is VRMS, which is equal to square root of 3 times of kb into t divided by m, and which is equal to 3 times of r into t divided by m, and which is equal to 3 times of p into v divided by m we shall consider. So this is about root mean square speed. And one more term we have to understand, that is most probable speed. So third one we can consider most probable speed, right? So most probable speed means speed of that maximum gas molecule, you can call it as most probable speed. For example, out of 10 gas molecule, if 8 gas molecules are moving with a speed of 8 meter per second, that speed we can consider that most probable speed here. That most probable speed v of m into p, which is equal to square root of 2 times of kb into t divided by m, or one more form 2 times of r into t divided by m, and another form we can take it as 2 times of p into v divided by m. So in order to express that speed of the gas molecule, we are having average speed, root mean square speed, and most probable speed. Out of these 3 speed, which one value is greater we can consider. So look at here, I will take use of this equation. Average speed I will consider. Look at here, average speed, which is equal to square root of 8 times of kb into t divided by pi into m, right? So to this equation I will make multiply and divide by 3. If I do like that, so average speed, which is equal to 3 times of kb into t divided by m, which is equal to what? 3 times of kb into t divided by m is nothing but VRMS. So I can consider 8 by 3 pi into VRMS. So if I calculate, nearly it is 0.92 times of VRMS. So average speed which is equal to 0.92 times of Vrms. And one more form we can consider, again the same thing, most probable speed which is equal to square root of 2 times of kb into t divided by m. To this equation again multiply and divide by 3 times of kb into t divided by m. Again this is also equal to Vrms, right? So most probable speed which is equal to square root of 2 divided by 3 into Vrms. So this is nearly equal to 0.8 into Vrms. So from this equation it clears that Vrms value is greater out of these three. Which value is greater here? Root means square speed value is greater than that of average speed, and this average speed is greater than that of most probable speed. So look at here, I got a conclusion here. Vrms is greater than that of average speed, and average speed is greater than that of most probable speed. So out of these three we got that Vrms value is greater than that of average speed and as well as most probable speed here. So hope you get this thing. We'll go for next thing. So in case of that gas molecule, the total pressure exerted by the gas molecule which is equal to sum of the individual. The total pressure exerted by the gas molecule is equal to sum of the individual, I said. So this is explained by Dalton. So that is Dalton's law of partial pressure. So according to that, Dalton's law of partial pressure, total pressure exerted by the gas molecule which is equal to sum of the individual. So mathematical expression for Dalton's law of partial pressure we can consider. Dalton's law of partial pressure. Right? So total pressure exerted by the gas molecule which is equal to sum of the individual, right? P which is equal to n1 plus of n2 to so of n of n kb into T. So this is about Dalton's law of partial pressure. So remember this equation. Then so already we discussed that degrees of freedom in case of thermodynamics. Now let me focus in depth about that degrees of freedom. Degrees of freedom. What's the mean of this degrees of freedom? The number of independent variables which can describe the position of the object, we can call it as degrees of freedom. What's the mean of degrees of freedom? The number of independent variables which describes the position of the object, we can call it as degrees of freedom, right? Then we have the direct connecting formula to find the degrees of freedom. So F which is equal to 3n minus of k. So this is the connecting formula for the finding out that degrees of freedom for monatomic, diatomic and for triatomic gas. F stands for degrees of freedom. Right? Whereas n stands for number of molecules, or we can call that n stands for number of atoms. Where k stands for, we can consider that number of independent relations. Number of independent relations. K stands for number of independent relations, right? Then for monoatomic gas, how many degrees of freedom we shall consider? First thing, for monoatomic gas, right? So for monoatomic gas, how many degrees of freedoms are present? For monoatomic gas, right? For that monoatomic gas, n value is 1. Mono means single, n value is 1, k value is 0. Then F, which is equal to 3 into 1 minus of 0. So for monoatomic gas, how many degrees of freedoms are there? So for monoatomic gas, degrees of freedoms are 3. And for diatomic gas, for diatomic gas, N stands for number of atoms, di means 2. Number of independent relations. So look at here, for monoatomic gas we require that 3 degrees of freedom. For diatomic gas 6 degrees of freedom, right? So for single atom 3 degrees of freedom, for another atom 3 degrees of freedom. Out of 6, 1 is act as common axis, so k value is 1 for diatomic gas. Then F, which is equal to, so degrees of freedom for diatomic gas is 5. Then for triatomic gas, in case of that dealing with the triatomic gas, we can consider that linear molecules and non-linear molecules for triatomic gas. Right? For triatomic gas, for non-linear molecule, let me take 3 molecules non-linear. So here 3 independent relations we get. So n value is 3 and k value is also 3 for non-linear. F, which is equal to, so degrees of freedom for triatomic gas in case of non-linear molecule is 6, and for linear molecule 3 molecules are arranged linearly. Then number of independent relations are 2. N value is 3 and k value is 2, means F value is 7. So degrees of freedom for triatomic gas, linear molecule is 7, for non-linear molecule is 6. So hope you get this thing, and then next we'll understand about that. Law of equipartition of energy. So according to that law of equipartition of energy, look at here, next we'll understand about that law of equipartitions of energy. Of energy. So if the gas molecule is in equilibrium position, so listen here, according to that law of equipartition of energy, if the gas molecule is in equilibrium, total energy of the gas molecule is distributed in all degrees of freedom. So listen here, in case of that gas molecule, if the gas molecule is equilibrium, the total energy of the gas molecule is distributed in all degrees of freedom. Then each degrees of freedom having that energy, kinetic energy of each degrees of freedom along x-axis, along y-axis and along z-axis, kinetic energy of each degrees of freedom, which is equal to half of kb into t. So this is about that law of equipartition of the energy. If a system is in equilibrium, total energy is distributed in all degrees of freedom, then each degrees of freedom having that energy half of kb into t. So this is about law of equipartition of energy. And lastly we can discuss about that. So mean free path, it is represented by the symbol lambda. So mean free path means the average distance traveled by the gas molecule between two successive collision, we can call it as mean free path. What is mean free path here? The average distance traveled by the gas molecule between two successive collision. Then after deriving you will have the equation. So 1 divided by √2 times of n into pi into d square, where d is distance between the gas molecule. So this equation I have to rewrite in terms of mass. So m divided by √2 times of rho into pi into d square and we have that one more form, that is lambda, which is equal to kb into t divided by root 2 times of pi into p into d square. These are all different forms of mean free path. Mean free path means the average distance traveled by the gas molecule between two successive collision.